We now look at a two-dimensional discrete system, see how we can find equilibria and determine the stability. So let's look at the first problem. To find the fixed point, we remove those subscripts t or t plus 1. So that's what we have. So for first problem, we just let x to be x plus y, and y is going to be 2x plus y. So this is called find fixed point. And from here we can see easily y is equal to 0. And then when we plug into the second equation, we see 2x is also equal to 0. So we have an equilibrium, x star y star is equal to 0, 0. Okay. It's a fixed point. Now how can we determine the stability? We still have two functions. One, we have fxy is equal to x plus y. That's from the first one. And then we also have the second one. And we have g of xy is equal to 2x plus y. Just like the continuous case, we take the partial derivatives. And then we have 1. Partial derivatives back to y is also 1. And we have a matrix. Because this is a simple dynamical system, we don't have x, y in the derivative. We just have a matrix of constants. And then we find its eigenvalues. We do the same thing. Find what's going to be the determinant of lambda I minus a. And that's going to be lambda minus 1, minus 1, minus 2, lambda minus 1. And then from here we have lambda minus 1 squared minus 2 is equal to 0. So we have two. If we look at this equation over here, we have two solutions. Lambda minus 1 squared is equal to 2. So lambda minus 1 is equal to plus minus root 2. And lambda 1, we have 1 plus root 2, which is bigger than 1. We say bigger than 1. And lambda 2, we have 1 minus root 2 is less than 1. So this is a saddle. So x star y star equal to 0, 0 is a saddle. It's unstable. And unstable. Now let's look at the other example. This is usually called a difference equation. We have xn plus 2 minus xn plus 1 and minus 6xn equal to 0. It's a special form really of the difference system of differential system of a special case of the discrete system. In fact, we can do the following thing. We can say, we can call xn plus 1 to be yn, and then xn plus 2 is going to be yn plus 1. So the system actually we have is yn plus 1 minus yn minus 6n is equal to 0, and xn plus 1 is equal to yn. Or we can say we have xn plus 1 is equal to y sub n, and yn plus 1 is equal to 6x sub n and plus yn. So we see this is always possible. But on the other hand, it's not necessary to do so if we just want to find an equilibrium and determine the stability. We can just start from the second, this is called degree 2 difference equation, and we do exact same thing. Find fixed point. That means we remove the index and solve x star. And then we have negative x star equal to 0, so x star is equal to 0. So this is our equilibrium. And how to find the stability? We have a way of doing that. We look at so-called its characteristic equation. We replace xn plus 2 by lambda squared, and next one by lambda, and then the next one over there is just negative 6. This is called its characteristic equation. In fact, this is exactly the equation you get if you actually find the determinant of this lambda I minus a for the linear system over here. So then from here we can actually see this is lambda minus 3 and lambda plus 2 is equal to 0. We have two, you can still call them eigenvalues. Lambda 1 is equal to 3 and lambda 2 is equal to negative 2. Now if you look at their absolute value, they are all bigger than 1. Doesn't matter if it's the first one and second one. So that means this x star is unstable. It is a repeller. And that's all for the stability discussion of equilibria.